Hello and welcome everybody. Today in calculus, we will be looking at section 7.3, which is on trig substitution. Now this section, we're going to have to break it into two parts because it is a little dense, and I want to make sure that we can get through this as thoroughly as possible. So without further ado, let's go ahead and get started. Now, when it comes to trig substitution, what we need to do is we need to work with the identities that we had back in pre-calculus slash trig. Now, there are technically a whole bunch of them, but the only ones we really need are the two that I have underneath over here. So if you have sine squared plus cosine squared is equal to 1, and also 1 plus tangent squared plus, is equal to secant squared. Anything outside of these Pythagorean identities, it's really not necessary. So let's go ahead and dive into it and see how this actually works out then, okay? Now, here in my first example, we have the integral of 1 divided by square root of 1 minus x squared dx. Now, just for sake of argument, I know that this is going to be equal to secant inverse, but for some reason, let's just say that you did not remember that because, well, maybe the day before you just kind of like forgot it or whatever, right? Or maybe you just never even learned it. We'll see how it goes. Here's what I'm going to notice then, okay? I am going to look at the bottom part over here where you notice that we have 1 minus x squared. Now, there is a trig substitution that I can make according to my two Pythagorean identity over there. If you look at the two form, which one can be rewritten in the form of like 1 minus x squared? I am looking at the first one over here. I'm looking at the first one over there because you can take that identity and write it so that it's maybe like saying 1 minus cosine squared is equal to sine squared, or 1 minus sine squared is equal to cosine squared. So let me just kind of write that to show you. So 1 minus cosine squared is equal to sine squared. Or you can write 1 minus sine squared is equal to cosine squared. So what that means now is I'm going to go ahead and try to make a u substitution or a x substitution that is similar to that in the numerator. So here, what I'm going to say is the following then. Let x, which is in the bottom over there, be equal to either one of those two equations. Doesn't really matter which one. I'm going to go ahead and use sine because, well, cosine is just going to be its derivative, which is nice and simple. If you do it the other way around, it'll still come out to be the same answer in the end. So if x is equal to sine of theta, then that means that dx would then be equal to cosine of theta d theta. Now, going back to my original, I'm going to now make a replacement for all the x's so that it's in terms of theta then. So my now integral is going to say, let's go ahead and take care of the dx part right there. Dx is supposed to be equal to cosine of theta multiplied by d theta, all divided by the bottom part. Now, when I make that substitution, it's now going to say 1 minus x gets replaced by sine, so it's 1 minus sine squared of theta. So we now have to clean this up a little bit before we take the integral. So that is going to be equal to the integral of cosine of theta times d theta, all divided by the bottom part, the square root of 1 minus sine squared. Well, that's the same thing as cosine squared. So if I make that go down on the bottom, you'll see how it comes out kind of nice and clean because now the bottom is just going to be cosine and the top is just going to be cosine, and then we have d theta, and that is pretty nice because that is just equal to 1. Now be careful about this part. We are taking the integral of 1 d theta. So that means our answer is equal to theta plus c because theta is our variable. Okay, remember we're not using x yet. So the final step is to go back and replace theta with what it's supposed to be. Well, if you recall from our substitution over here, x is supposed to be equal to sine of theta. So then that means if I want theta, theta is going to be equal to the sine inverse of x. So that right there is going to be my final answer. So this right here is the general idea behind the trig substitution. We're supposed to use one of those two identities and then make a replacement. So then that way we get a trig substitution. And it's going to be some sort of trig integration, just like in the last section then, okay? All right, now let's go ahead and look into something a little bit more complex and see how that works out over here, okay? So this time we have the integral from 1 over root 3 to 1 of 2 dx, all divided by z times the square root of 4z squared minus 1. These are some things that should look somewhat familiar to you, because if you look at it as a whole, you can hopefully recognize that this is going to be some sort of secant inverse of something. In terms of what that something is supposed to be equal 2z, and then it's going to be 1 over 2. I select these problems just to make sure that we can get an answer that we can, basically recognize it from the very beginning. But again, just in case we forgot the antiderivative of this equation is supposed to be secant inverse, let's go ahead and use this trig substitution to work our way out. Okay. So here again, what I'm going to notice is the bottom part over here, which is 4z squared minus 1. Now, which one is going to give me something squared minus 1? Something squared minus 1? Well, that is probably going to be this guy right here, because if you take my second equation over here, my second identity, I can rewrite this as tangent squared is equal to secant squared theta minus 1. Okay, on this equation, you'll notice that we have kind of like something that is parallel to the right-hand side, secant squared minus 1. So what that tells me is the following is going to be my substitution then. Okay, secant of theta is going to be equal to 2z in this case, right? Because in the inside over here, I can rewrite that as 2z quantity squared minus 1. And that's how you can kind of see how it matches up over here in this case. All right, so that is going to be my substitution. Now we're going to go ahead and take the derivative so we can do some sort of a chain rule to this. So that means now 2 dz is equal to secant of theta times the tangent of theta multiplied by d theta. So taking the derivative of both sides, that's going to be my substitution then. Okay, now we're going to go back to my original equation. Let's go ahead and change the boundary, because remember, this is in terms of theta. So let's see. In the first part, let me go ahead and write on the side my 1 over root 3, and keep in mind, we're going to be looking at this guy over here, multiplied by 2 is equal to secant of theta. So that means that we have 2 over root 3 is equal to secant of theta. So that means that cosine of theta is equal to root 3 over 2. So that tells me my lower bound is going to be pi over 6 then. And similarly, my upper bound, it's 2 multiplied by 1 is equal to secant of theta, because that's my substitution. So let's see, 1/2 is equal to cosine of theta. So that means that theta is going to be equal to pi over 3. So that is going to be my upper bound. Okay, now according to my substitution, let's go ahead and replace each part then. For the bottom part, okay, so inside the square root, because I think that one is pretty straightforward, hopefully. Well, actually, maybe it's not very straightforward. So let's see. If we make that replacement as we said, it's going to be the square root of, okay, let's see. It looks like it's going to be secant squared theta, okay, minus 1. Because remember, 2z is equal to secant of theta, okay? So that's the inside of the square root. Now, for the outside, you'll notice that we have a z over here, and that needs to get replaced too. So that looks like it's going to be equal to secant of theta divided by 2. Whereas the numerator, we still have the 2. And then now we have to multiply by dz, which is going to be the bottom piece that is over here. So we're going to go ahead and put that in now. So let's see here. dz is going to be equal to 1 over 2, because we need to take this 2 and move it over to the other side. And then we also have the secant of theta times the tangent of theta times d theta. Okay, so don't forget the d theta part, because that is important for our integration. Okay, so our job is to clean this up as much as possible, and then hopefully we can solve for this finite integration. So the 2 and the 1/2, they can cancel each other out. Let's see, let me just go ahead and rewrite the boundary. So pi over 6 to pi over 3. The top part, we still have, oh wait, actually, let's see a little bit more. I see secant of theta and secant of theta cancel each other out. So that actually works out pretty well too. Let's see, anything else? Not really. So let's see, we're going to have the tangent of theta on top. okay? Divided by, and then we have d theta 2. Now this 2 right here, since it's in the reciprocal's reciprocal, then we might as well say that it's on top then. So I'm going to go ahead and write up on top over there. The square root of secant squared minus 1. Well, according to what we have right here, it's supposed to be tangent squared. And since it's under the square root, then that means that it's going to be straight up tangent then. So that works out pretty nicely. Once again, the tangents are going to cancel each other out. So that leaves me with just the integral of pi over 6 to pi over 3 of 2d theta. Taking the antiderivative is going to give me 2 theta, and then boundary from pi over 6 to pi over 3. Now again, because we have our boundaries changed, we don't have to replace it back into terms of z. So we can just literally make a substitution here. So my final answer is 2 multiplied by pi over 3, that's my upper bound, minus 2 multiplied by pi over 6, that's going to be my lower bound. So that looks like it's going to be 2 multiplied by pi over 3 minus pi over 6. Which gives me 2 multiplied by pi over 6. So the answer is equal to pi over 3 then. Okay. Now let's go ahead and maybe look at one final example over here where things are going to be pretty nasty because if you notice, this one, well, unfortunately, we don't have a nice, I guess sum of squared as we normally would, or difference of squares we normally would. So if you look at the denominator of this problem right here, we have 5x squared plus 6. But we can still treat it the same way because we still have, if we kind of like force it, we still have some sort of like sum of square that we can kind of work with. Okay, so first off, what I'm going to do is, again, look at the right-hand side and look at which two of these identities we'll be using in this case. I want something squared plus 6, or something squared plus 1. So that tells me it's most likely going to be this guy over here that is going to be on the bottom, because that is going to be the only one where it's like a constant plus a trig function squared, or like say, in this case, a variable squared. All right, so let's go ahead and see if we can focus on certain parts of this. Now, just to kind of rewrite it so you can see it a little bit better, I see this as the square root of 5 quantity x squared, and then plus the square root of 6 quantity squared, if that helps you kind of see it a little bit better, okay? So what that tells me is that I probably need to make some sort of substitution for the square root of 5 multiplied by x. And then that is supposed to be equal to some sort of tangent of theta, okay? Now, if we were to use this as our substitution, let's just see what happens if I plug it in just to make sure that we get the result that we want. If we make that substitution, the inside of the square root, it's going to say tangent squared theta and then plus 6. Now that right there, I do have a slight problem because I want tangent squared theta plus 1. So what that means is I actually need something over here to kind of compensate for that 6. And that something is where that root 6 comes in. So what I need is actually going to be the following. I need root 5 times x is equal to root 6 times tangent of theta. So then that way when I square both sides, that way I'll have that 6 tangent squared theta plus 6. And that is what's going to allow me to get rid of all of those nasty parts. Okay, so there it is. That is going to be my substitution. Okay, let's go ahead now and do my replacement then, or actually not replacement yet. We're going to go ahead and take the derivative because we have to do kind of like, again, U-trig substitution. So root 5 multiplied by dx is equal to root 6 multiplied by the secant squared theta d theta. Okay, now let's go ahead and make our substitution as we were saying earlier. The integral, now this is going to be kind of nasty here, so just, bear with me. The top part, we have x cubed. So let me go ahead and take this guy right here and solve for x cubed then. So that's going to be x is equal to root 6 divided by root 5 multiplied by the tangent of theta. So if I cube both sides, then x cubed is going to be 6 over 5 raised to the power of 3 divided by 2, just rewriting the root as a 1/2 power. And then we have the tangent cube of theta. So that's going to be on the top. So 6 over 5 raised to the power of 3/2 multiplied by the tangent cube of theta. And don't worry about that constant part. I know it's nasty, but more worry about the trig part to make sure things actually cancels out. Okay, next piece. We're going to go ahead and make a replacement for dx. So that's where this guy over here comes in. So if I want dx by itself, we're going to have to take this root 5 and put it over here on the bottom side of the right-hand side. So that's going to give me root 6 divided by root 5 multiplied by the secant squared of theta d theta. Okay, and hopefully you can kind of see that the constant that has been extracted over here and the constant I had earlier with the 6 over 5 to the power of 3 over 2, those are going to cancel out nicely then. Now let's look at the denominator, this big nasty part that I was going to replace. Well, earlier we said that that's where this guy is going to come in. So that's going to be my replacement. So it's going to be the square root of 6 times the tangent squared of theta and then plus 6. Now we're going to go ahead and clean up using algebra and hopefully it does come out nicely. Let's see. So that's going to be the integral. The bottom part, okay, the bottom part, as much as I hate to do it, we got to take care of it soon. I'm going to go ahead and take out the square root. Actually, no, I'm going to go ahead and take out the 6 part, okay? And then that's going to give me the tangent squared of theta plus 1. Now, the top part, if you remember earlier, we said this guy right here and this guy right here, they can mesh together. This, to me, that's going to be the same thing as 6 over 5 raised to the 1/2 power. So if you have those two multiplied together, that actually works out nicely because then that means we have 6 over 5 raised to the 3/2, 6 over 5 raised to the 1/2. So combine that two together, that is going to give me 6 squared over 5 squared. So a lot of algebra work in this case. Then we also have the tangent cube of theta, so that's nice. Then we also have the secant squared of theta, not so nice, and then d theta. Okay, keep cleaning things up. Okay, we have the integral. The top part will still have the tangent cube. The bottom part, we're going to go ahead and take out the square root of 6, and then we have 36 over 25. And then this over here, where we have the square root of tangent squared plus 1, that is going to be equal to secant squared of theta. And then we're going to have that inside the square root. So that is just going to be plain old secant of theta. And what always or most of the times happens is that you're going to have something on the bottom, a trig function, that is going to cancel out with the trig function that you're going to create because of the u substitution that's over here. They don't always cancel out perfectly, but they have something that should always try to cancel out. Okay, so let me just go ahead and check my progress, make sure everything is okay, and yes, they look okay. So let's go ahead and move on. Okay, let's see. We're going to go ahead and write the 36 over 25 root 6. And then the integral, let's see, the secant of theta cancel out with one of the secant of theta. So that means that we have the tangent cube of theta multiplied by the secant of theta. And this is where we're going to run into a little bit of trouble because this is now recalling something from the last section where we have to use, where we have to integrate trig equations then, or trig expressions. Okay, so the way that we're going to handle this one is to write as the following. 36 divided by 25 root 6 integral, I see we have tangents cube and then we have secant of theta. So I'm going to go ahead and write it as the tangent of squared theta. And then we also have multiplied by the secant of theta times the tangent of theta. So let me go ahead and squeeze that in there. Okay, d theta. Because what can happen now is that the tangent squared can be replaced by secant squared minus 1. So 36 divided by 25 times the root 6. And then the integral of secant squared minus 1. And then we also have secant of theta times the tangent of theta. And if you recall correctly, my u substitution in this case is going to be equal to secant of theta because du is equal to secant theta tangent theta. That's the reason why I wrote it in that form from earlier. All right, so let's see. If I make that substitution, we have 36 divided by 25 root 6. The integral of u squared minus 1, and then we have du. So that comes out to become somewhat nice and clean. So let's see, 36 divided by 25 root 6. And then this is going to be 1/3 u cubed minus u, and then we have plus c. Change back the u so that it's in terms of secant. So 36 divided by 25 root 6. And then we have 1/3 multiplied by secant cubed of theta, and then minus secant theta, and then plus c. And remember, we're not quite done because we need to change those thetas back into x's. So that's where this guy over here comes in then. Okay, so let me go ahead and draw this on the bottom over here just in case. Our equation, and let me just go and write on top, is supposed to be root 5x is equal to root 6 that is tangent of theta. I need to use this substitution and somehow solve for what is secant of theta. Well, let's see. Let me go ahead and move some stuff over so we can go ahead and set up a right triangle for this. So this is now going to say root 5x divided by root 6 is equal to the tangent of theta. For my right triangle, here's what this is going to look like. So here's going to be my angle theta. Tangent is supposed to be opposite over adjacent. So that means that this is going to be my root 5x, and then my adjacent is going to be root 6 then. So using the Pythagorean theorem, this guy right here, the hypotenuse, is going to be 5x squared, and then we have plus 6, and all of that is going to be inside the square root then. So now according to this triangle that I just drew, I need to figure out what is secant of theta. Secant of theta is supposed to be equal to 1 over cosine, so that means it's the hypotenuse and the adjacent that's involved. More specifically, it's the adjacent over, not the adjacent over hypotenuse over adjacent. So then that means it's going to be the square root of 5x squared plus 6, all divided by root 6 then. So my final answer is going to be 36 divided by 25 root 6 multiplied by 1/3 multiplied by the secant cube. So then that means is 5x squared plus 6 divided by 6 raised to the power of 3 over 2. And then minus 5x squared plus 6 over 6 raised to the power of 1/2. And then we have the plus c. So there you go. That's going to be our nasty problem of the day then. All right. Well, thank you so much for watching. I will see you guys next time then. Okay, take care. Bye-bye.